I welcome all participants of conference. The report on that is offered to your attention: scientific and technical problems of transition from open pit to combined technologies for raw materials mining. In terms of explored iron ore reserves, Ukraine ranks second among the most powerful mining countries. The main reserves of iron ores are located on the Ukrainian crystalline shield in Kryvyi Rih iron ore basin. This basin, along with Kremenchuk and Belozersk iron ore districts, forms the region of Greater Kryvyi Rih or Kryvyi Rih iron ore basin, Kryvbas. Iron ores are represented mainly by three geological and industrial types: rich magnetite, hematite, martite ores, ferruginous quartzites, and light brown iron ores. Of the total volume of iron ore raw materials mined in Ukraine, Kryvbas accounts for about 80%, at that the share of the open pit mining method is about 70–80%. Ferruginous quartzites are mined mainly by open pit and partly underground methods. The dynamics of iron ore production by mining enterprises of Ukraine over the past 10 years is shown in Figure 1. The open pit method of mining causes alienation of much more land. In Kryvyi Rih basin, which accounts for up to 85% of marketable iron ore raw materials production in Ukraine, mining has disturbed thousands of hectares of fertile arable land. According to the State Enterprise State Institute for Design of Mining Enterprises Kryvbas project, in Kryvyi Rih basin land expenditure per unit of marketable products is 13 times larger when applying open pit mining methods than in underground mining. Air pollution by dust and gas emissions is also much greater as compared to underground works. During open pit mining, the damage caused to the environment per 1 tons of marketable products is 3.5 times greater than in underground mining, and considering the quality of marketable products, it is 3 times larger. The above-mentioned conditions of iron ore deposits operation and their impact on the environment deterioration when applying the open pit mining method are summarized. Table 1. According to, every 1,000 tons of rock mass mined by mining and processing plants produces just about 200 tons of iron ore products. At that, 40 meters square of land is alienated and 50 meters square of land is flooded. 110 meters cubic of highly mineralized waters is consumed. 2.5 tons of fine dust and 1.8 tons of poisonous gases are emitted into the atmosphere. As compared to the open pit methods, underground mining of deposits demonstrates the following significant environmental advantages: reduction of area losses caused by formation of open pits and waste dumps, possible separate extraction of rich iron ores of different varieties, use of overburden rocks as raw materials for byproduct production, lower losses of ore raw materials in the subsoil, possible creation of nature reserve areas, recreational areas after completion of the deposit operation. Thus, one of the main ways to reduce the negative impact of open pit mining on the environment of the basin consists in gradual transition from the open pit mining of mineral deposits to environmentally friendly technologies of open pit underground and underground mining. Such a transition is found to be a forced and at the same time choiceless way of developing mining areas, in particular Kryvyi Rih iron ore basin. The main problems of such transition will include those of geomechanical stabilization of the rock massif during construction of underground mines and areas of possible impact of open pit fields. Combined open pit underground mining allows for maintaining the production capacity of mining enterprises for a long time. Along with that, introduction of scientific recommendations and technological solutions for combined mining of reserves has enabled a number of foreign companies that traditionally applied the open pit method to involve areas of deposits considered unpromising into intensive operation. The Kiruna mine is the world's largest and most modern mine with open pit underground iron ore mining. Figure 2. The mine is located in Kiruna, Sweden, and owned by the Swedish mining company Luossavaara Kirunavaara. In 2018, the mine produced 26.9 million tons of iron ore. Until the 1960s, the mine applied the open pit ore mining method. Now iron ores are mined by the underground method. Based on the analysis performed, it is established that the choice of combined mining technology is to a great extent impacted by the stress-strain state of the rock massif. Mathematical methods enable assessing current conditions and obtaining predicted data for enhancement and development of new mining methods, improvement of the flow sheet, selection of optimal parameters for stoping. Consequently, a comprehensive assessment of values of current stresses in the massif, prediction of their nature and causes of their change during combined open pit underground and underground stoping are necessary. This information will enable assessing current conditions and obtaining initial data for improvement of the applied and development of new combined flow sheets of open-pit underground mining, selecting optimal parameters for stoping operations and determining their rational sequence. In this paper, SolidWorks 2015 software is used to determine the intense deformed condition of a rock massif related to the determination of the stress field. To calculate the stress-strain state of the combined massif, options of the classical scheme of open-pit underground mining of magnetite quartzites are accepted for the average statistical conditions of transition from open-pit to underground mining. A grid of finite elements of the initial design model is given in Figure 3. The model is adequate in size to the site where the technology under study is applied and is used to calculate stresses during open-pit underground mining. Isolines of the main stress field around the rooms with an open stopping space and rooms backfilled with a consolidating mixture and collapsed waste rocks are presented in Figure 4. To visually determine the stresses, all isolines have a certain stress value in Pascal and correspond to a certain color scale. The idea behind the first flow sheet of transition from the open pit to underground method of mining an ore deposit is illustrated in Figure 4. After the complete drawing of the broken ore, the stopping space of the worked-out room is filled with waste rocks resulted from driving underground and open workings. The calculated isolines of the main stresses of the rock massif when applying open-pit underground mining of the magnetite quartzites deposit with ore breaking and drawing and subsequent backfilling the stopping space of the worked-out room with waste rocks are presented in Figure 4. As is seen in Figure 4, the general picture of the distribution of the field of stresses is classic. The greatest absolute magnitude of stress occurs near the angles of the formed stope from the side of the ore massif. Small concentration of stresses is observed in the corners on the bottom of the room. Significant maximum stresses in the corners of the room appear due to the action of compressive stresses. The stresses decrease depthward into the ore massif and their distribution becomes more uniform. Concentration of maximum stresses is observed in the upper and lower corners of the rooms that are not backfilled, and only in the lower part of the backfilled ones. In some cases, lateral exposures of the infilled stope may be distinguished by the fact that tensile stresses appear in the central part of the lateral generatrix. In this case, stresses 1 are reduced from the boundary of the room depthward into the ore massif. The idea behind the first flow sheet of transition from the open pit to underground method of mining an ore deposit is illustrated in Figure 5. In addition, the proposed solution to store waste rocks in the worked-up space of underground mines has a significant environmental effect, improving the environment of the mining basin. In the future, in order to develop the environmental safety of the region, it is proposed to store all available waste rock, including overburden at possible parallel ore mining by the open pit method, in the worked-up space of underground mines. Further underground extraction of magnetite quartzites will be carried out by systems of level caving of ore under overlying waste rocks. This technology is the cheapest due to no consolidating backfill used that is provided for in the following flow sheets. Conclusions. It is determined that nowadays development of deposits of ferruginous quartzites of cribas by underground mining has equaled the cost of open pit operations. At the same time, the cost of open pit operations will steadily increase, but in underground mining it will remain rather stable. The nature of distribution of the maximum stresses in the massif is determined. Mathematical modeling is performed and the results of calculating the main stresses are presented in the proposed variations of the open pit underground mining of the magnetite quartzites deposit. It is proved that transition to open pit underground and over time to underground mining will reduce environmental tensions in the region. Highly efficient technologies of transition from open pit extraction of magnetite quartzites to open pit underground and underground mining of iron ore raw materials within the mining basins of Ukraine are developed and improved. Thanks for attention.